another one of our participating departments. He's the director of the Computational Applied Science and Engineering Lab. And he specializes on high-performance numerical methods in search of optimal solutions to a variety of problems. In particular, this search for optimal solutions leads him to solve both forward and inverse problems, and high-performance search of design spaces is obviously critical to finding optimal solutions. So he's interested in design, and in a recent application of his work into shape-shifting structures, and in a previous work focused more on optimal bio-inspired swimmers. So today, Wim is going to tell us about flow simulations for bio-inspired underwater devices.
Thank you, Nicholas. Thank you for the introduction, and thank you, Nicholas and Yusuf, for allowing me to talk on this symposium. So I'm going to show a little bit of the motivation that is behind our work, as well as some previous results, but the main focus of my talk will be on some numerical methodology that we have developed in the lab to simulate flows with embedded boundaries and sharp interface approaches. So I'm assistant professor. I've been at MIT for 3.5 years now. I'm in the Department of Mechanical Engineering in the area of ocean engineering. And so my motivation comes from looking at challenges in the ocean and opportunities in the ocean. So we have a lot of things that are threatening, the ocean environment, including microplastics, algae blooms, coral bleaching. But we also have opportunities for using the ocean for solving some of our societal problems. So offshore aquaculture is a potential solution to some of our future food shortages. Energy harvesting is a way to use the ocean to solve some of our energy problems. And we have a lot of kind of exploration to do in the ocean, because there's vast parts of the oceans, including all sorts of organisms there that we don't know about yet. And so there's a lot of challenges and opportunities in the ocean. And some of the ways that we can tackle these are by taking some inspiration from how nature operates in an ocean environment. And so here we get into bio-inspired devices. And so if we look at some of the swimmers that nature has evolved over millions and millions of years, we see that they combine a couple of interesting aspects. They combine soft materials typically. They combine actuation and sensing. They've arisen through evolutionary design, and they're able to learn and adapt. So they have a high amount of versatility and agility. And so that leads to all sorts of amazing feats in nature that they can achieve in the ocean that would be very useful for some of these applications to adopt in engineering approaches. So here, for instance, this fish has a lateral line here on the side that can sense pressure, and so it can adapt its actions based on what it senses in the flow. There's a lot of deformations here. There's passive deformations in these kind of swimmers. There's also active deformations. They have musculature that allows them to modulate the curvature of their fins. And here's an example of how a ray-finned fish in the tail of a fish, how they can pull on tendons to curve the tail actively against perhaps a hydrodynamic loading. So there's a lot of these things that are interesting to adopt. And at the same time, in engineering, we're seeing some developments that lead to the emergence of smart soft structures, such as additive manufacturing and other additive manufacturing techniques, and also optimization and AI that allows us to use more complex materials and more complex actuation mechanisms to get to aspire to some of these behaviors that we see in nature. And so that leads to underwater swimmers that, including this one from MIT CSIL, from Daniele Ressa's group. Here's a swimmer from Harvard University based on a stingray that's also using soft materials and very much inspired by nature. And here's some of my recent work where we're looking at structures that can change their shape in response to a stimulus, in this case, temperature. And so we printed a flat structure that morphed into a human face. I'm not going to talk about that today, but it's one of those developments that inspires me to look at how can we kind of use those degrees of freedom of actuation and how can we investigate these kind of smart, soft structures. And so my tool of choice is to use numerical simulations to explore essentially this vast parameter space. And so I've done a lot of work on optimization and reinforcement learning with self-propelled swimmers. So that basically starts from taking the Navier-Stokes equation, solving them in the presence of a deforming body and letting the body kind of swim in the fluid flow. And so we couple that to optimization approaches to find optimal kinematics of swimmers and optimal shapes of swimmers. And that allows us to uncover kind of optimality in nature and look at what performs well for a certain task. And here is an example of reinforcement learning from my PhD group in Zurich, where we trained a swimmer to follow another swimmer in a flow domain, right? And so here we're using reinforcement learning to uncover the policy that gets us, in some sense, to an optimal solution behaviorally. And then more recently, we're also looking at more the physics side of things. We're looking at how curvature variations affect flapping foil propulsion. So here's a flapping fin that models essentially the tail of a fish, and we're making it flap with different amounts of curvatures, chordwise curvatures, and looking at efficiency and thrust enhancements with either curving against the flow or curving with the flow. And then we can do the same thing in 3D to find the effect of both chordwise and spanwise curvature variations in a fluid flow. So that's kind of the overall picture in which I'm developing numerical methods for solving these types of equations. Now, what I'm going to talk about today is a new implementation that we have developed of the 2D vorticity velocity Navier-Stokes equations using the immersed interface method. So I'll talk a little bit about the immersed interface method and how we use that to discretize a boundary that is not aligned with any of the grid lines in the domain. And I'm going to talk a little bit about how to numerically solve the vorticity velocity form of the Navier-Stokes equations and what are the advantages of doing so. Why are we doing that? So this is different from the movies I showed on the previous slide. There we use a different approach. We're moving towards this approach because I'd like to start using a sharp interface treatment to couple our kind of flow problems to other physics problems like fluid structure interaction and multi-phase flow. And a sharp interface treatment facilitates that. I also want to move towards higher order time integration to provide more accuracy for two-way coupled flow problems where, for instance, in a fish, we want to solve the motion of the fish due to the flow forces, and we want to solve the flow evolution due to the motion of the fish. So there's a two-way coupling there that with low order time integration just doesn't get you very far. And so those are some of the motivations for moving towards this direction. I also am currently working with my group on extending all of this to 3 dimensions. So all of this stuff is James Gabbard's work, by the way, and he's part of this symposium. He's hanging around probably in the Gather town. So he's the expert on all of this project. I'm also working on the extension to 3D, and here we're building an adaptive grid refinement software framework that uses wavelets to maintain some consistency between different scales. And we're implementing that in an HPC architecture. So if I have a couple minutes at the end, I'll try to say some words about that. That is under progress, and that is Thomas, who is working on that. He's a postdoc in my group, and he should also be in the symposium. So shout out to these two. They're behind all of the work I'm presenting today. Okay, so let's take a little step back and talk about this immersed interface method. And if I take another step back from the immersed interface method and just look at how do we handle moving boundaries in a fluid flow, there's a couple of different computational techniques. Broadly, roughly, we can distinguish them in 2 categories. One is body-fitted meshes, where the mesh conforms to the body boundary. And this is often what you see in unstructured meshes, where, for instance, we have a body here that is moving and the mesh is always aligned with the boundary of the body. And so as the body is moving, we have to update the mesh. That is really nice because it gives you very high order accuracy near the wall. And it gives you an easy way to implement boundary conditions. But it can be very expensive, and depending on the body shape and the motion, it cannot be fully automated sometimes. So if this body would be rotating, you would get into a lot of trouble with just kind of trying to adapt the mesh accordingly. And so you'd have to come up with other techniques. Then over the last 2 or 3 decades or so, the immersed boundary methods have come into play, and they are basically representing the geometry independently from the mesh. And so we're working with a Cartesian mesh here or any other kind of structured grid that is not conforming to the boundary of the body. And the body is just kind of doing its thing around it. And we're taking into account the boundary conditions on the body algorithmically rather than geometrically. Okay. And so what that allows you to do is that you can decouple the mesh generation and also the adaptation from the geometry of the body and also from the motion of the body. So that gives you a lot of freedom to handle complex shapes, including the type of swimmers that we're interested in. The problem with this is that high fidelity solvers are much more complex to create, especially when you're looking at local near wall kind of solution variables, such as in fluid structure interaction problems or in multi-phase flows, where local features of the flow can determine the behavior of your essentially other physics component, whether it's another flow or whether it's the mechanics of the body. And so that's a little bit more tricky to implement, but there's, I'm going to present one way that we have solved this over the last couple of years. And there exist other ways as well to handle this with different advantages and disadvantages. So specifically, we've moved towards an immersed interface method. And that one can be classified as a discrete forcing immersed boundary method. So the continuous forcing immersed boundary method is not something I'll talk about today. It's what all my previous work is based on, but it's not something that gives us the advantages that we're looking for here. So the discrete forcing immersed boundary method, we're going to consider immersed interface as one of the features of one of the components of that. Okay, so this is a little bit more of a specialized slide for those of you more aware of this technique. So the immersed interface method has been developed by Lee and coworkers in early 2000s. Or actually even earlier in the early 90s specifically for problems that have jump discontinuities. So here's a function in 1D that lives on a regular grid. There's a boundary that sits between grid points, and the function has some sort of physics on the one side and some other physics on the other side. So think of this, for instance, as a membrane, an elastic membrane in a flow. So there's flow on both sides, but the solution to the problem has a jump discontinuity across the interface, and the interface can sit anywhere that is not on a regular. It can sit on a regular grid point, but also in between. And so the way that the immersed interface handles this problem is by taking a Taylor expansion, for instance, at point xi plus 1 around xi, and this is the normal Taylor expansion, and then we're correcting it using the jump discontinuity at the interface. And so the jump discontinuity is captured in these terms j, and they are functions of the actual jumps in the functions and its derivatives, right, up to n derivatives here. And so this formulation makes a lot of sense if your jumps here are the primary quantities that your interface kind of coupling is governed by. So either you solve for them or you know them, but you know something about these jumps. Now, when we are thinking about our flow problem, we don't have two physics on the side yet. We just have a kind of a solid body and a fluid flow. So we don't really care about the solution inside the body. We care about the fluid flow. And then we have some sort of boundary condition, maybe Dirichlet or Neumann, that sits on the interface. And so what people do in this case is they take this kind of picture, and rather than saying, oh, I'm going to extend the function, I have a physics on, let's say, the right side where the body is, I'm going to just set my function to 0 on the right side. And then I have to figure out what are my jumps in the function and the derivatives at the interface. And the jump is just the difference between the value on one side and the other side. So I have to find out my function values and all my derivatives on the boundary coming from the flow side. And that leads to a lot of computation to construct one-sided finite difference stencils to find all the derivatives on the boundary. But once you've done that, you can basically fall back to this approach and use the immersed interface method or the explicit jump immersed interface method to incorporate those jumps. So what James found when he worked at this is that basically this approach is identical to saying, oh, I'm going to construct a polynomial interpolation between my flow values and the boundary condition that sits on this immersed interface. And I'm going to evaluate that polynomial inside the body. And this gives me a set of jumps that I can, identically equal to whatever approach we found when we were doing this complicated approach of setting the domain with zeros and then solving for all the derivatives on the flow side. So this is what we end up doing, and it's identical to the standard kind of immersed interface method for complex domains, but it's much simpler because we just require one processing step here to construct a polynomial. Then we have filled function values on the kind of non-flow side of the boundary, and now we can apply finite difference stencils as if there was no boundary, and we have incorporated the boundary conditions in those. So that's really neat and pretty simple, and it kind of links IAM to standard kind of sharp interface immersed boundary methods. So what we do, for instance, in an example here in 2D, we have a body and then another body and then a flow in the middle. And so the first thing we do is we identify intersections between grid lines and the boundary. And those are all the intersections. Let's say we know boundary conditions on the body, so we know the solution value at these points. And then we use the boundary conditions to extrapolate inside the body. For instance, if we want to know the extrapolation inside this grid point, we're taking flow values from either side, either grid line, and constructing these 1D polynomial extrapolations or interpolations between the boundary value and the flow values and evaluating them inside the body. And so when we get information from two sides, we can do something by averaging the two directions, for instance. If we get information only from one side due to the geometry of the body, then we can just take the one side extrapolation. And so like this, we can also handle kind of concave parts of the bodies without really much additional difficulty here. And then once we have filled out those function values, we can apply finite difference operators and proceed our normal discretization. So this is what we do. When the boundary is moving, it's very simple as well. We just, once the boundary, for instance, moves away from moves into the top left corner, we just uncover this point and it becomes part of the flow now. And we know its value from the extrapolation. So there's no real issue between kind of stationary and moving boundaries here. Okay, so we take all of that and we combine it with vorticity velocity formulation of 2D Navier-Stokes. An advantage of doing this is that we can naturally include free space boundary conditions for external flows. So we don't have to worry about, kind of channel effects when you have free slip boundary conditions on either side of the obstacle. It's all free space just by the construction of the elliptic problem that we formulate. And that allows us to do very compact domains because we only need to worry about where is vorticity non-zero or significant. And that's the part of the domain that we are, keeping, that we are resolving. And it also allows us to explicitly conserve circulation, at least in the formulation that we have formulated here. Okay, and so there's been previous work on this, and that's basically the starting point of our work. But all these previous works are limited to stationary boundaries and single bodies. And so we've extended this to moving and also multiple bodies. And so if we just kind of formulate the problem here, we start with Navier-Stokes equation, divergence free, we have a boundary condition, and this is our kind of free space boundary conditions. U goes to a U infinity as X goes to infinity. And we can rewrite this problem in kind of three separate kind of vorticity velocity problems. One is velocity reconstruction that asks the problem, what is the velocity given the vorticity according to some boundary conditions on the body. One is transport, which is basically the curl of this equation. Which is a transport equation, right? So we have the transport equation for vorticity with a flux, an advective flux, and a diffusive flux. And so that's something neat about fluid mechanics, right? If you have vorticity in 2D here, it doesn't get created or destroyed in the flow, right? It can only be created on the boundary of the body, and that's the boundary condition on vorticity here. And then we have Kelvin's circulation theory, and I talk a little bit about that, but that's something that is relevant when you have a multiply connected domain as we have in 2D when there's one or more bodies inside. And so that needs to be enforced as well, which is basically conservation of circulation. Okay, so I'm going to go quickly through each of those steps, starting with the velocity reconstruction. This is essentially our elliptic problem, right? So normally the pressure reconstruction would be the elliptic problem of velocity pressure Navier-Stokes. This is our elliptic problem where we solve for velocity from vorticity. So the problem is to find the velocity given vorticity with a no-through boundary condition on the body. So it's almost like a potential flow problem here. And so typically we solve that by converting velocity to a scalar stream function, writing down a Poisson equation for that stream function with a boundary condition that is equivalent to the no-through flow. But if you do this, what you find is that you also need to solve for a global kind of constant per body. So you have an unknown on each body that is just a scalar that you need to find. And you can find that by adding an additional equation that is essentially the circulation, enforcing the circulation on that body. So we have a set of n equations for the number of bodies in the domain. And so, that's a little bit of an odd elliptic problem, but we can solve that. And that's a lot of that is Thomas Gillis's work from his previous group with Philippe Chatelain in Belgium. And so basically we use the immersed interface method to enforce boundary conditions on the irregularly shaped body. We consider the immersed interface method then a low-rank correction on a discrete kind of global free space Poisson solve. And that allows us to take a sure complement approach to solve essentially a small local elliptic problem for each obstacle to find the immersed interface corrections that satisfy the boundary conditions and the circulation. And then we can kind of combine it with a global elliptic solve to find the global field associated with those three equations here. And so the way we do that numerically is by using fast Fourier transforms with Dallas Green's functions for discrete consistency, and the GMRS and Krylov recycling approach for those local problems, so iterating through the local problems during each velocity reconstruction. Okay, so that gives us the velocity given vorticity and the circulation on each body. So then we can, we can validate that. This is a little example of what we can do with the IAM. So we have a test function here that is a vortex with these kind of weird shaped boundaries. We impose boundary conditions according to the solution, the free space solution of this vortex. So we know the boundary conditions, we know the solution, and we find second order average accuracy in this case pointwise, right? So in the infinity norm. So at any point here in the grid, we get second order accuracy, which is really one of the features of this sharp interface method that, as opposed to a lot of kind of continuous forcing immersed boundary techniques that only get first order locally. Okay, so then we have to evolve the vorticity field. For this, we use a set of conservative finite difference schemes to get a second and third order in space, third order in time, second or third, depending on whether advective or diffusive fluxes are dominant. And then we have a Dirichlet boundary condition on vorticity that essentially enforces no slip and results in the vorticity generation in the flow. One thing that is important here is this Kelvin's theorem. So if we use conservative finite difference schemes and we take any arbitrary rectangle in around, let's say, a piece of the flow, then we automatically enforce Kelvin's theorem discretely because of the conservative feature of the finite difference scheme. So we enforce a discrete equivalent of this conservation law. If we have a body inside, that's not automatically the case because there's a circulation on the body that kind of acts as another source here. And so what we do is we have to enforce conservation of circulation by introducing new state variables and then tracking the evolution equation for this circulation as a function of the flux of circulation you want going through this body. And then we can, at any point obtain the circulation around the body by just taking our state variable and subtracting the circulation of the domain, the flow, excluding the body, right? Okay, so we have a set of evolution equations. We solve vorticity, we evolve vorticity on each grid point. We evolve one circulation per essentially bounding box around each body. And that allows us to solve a feature of problems. So here's some examples. We can solve external flows, which is the flow here past the stationary cylinder, periodic flows, internal flows where we have an immersed kind of boundary that is inside the domain that is rectangular, but this flow is only solved inside this immersed surface. And all of the grids here are just Cartesian structure. We can solve multiple bodies by just having circulation tracking around each body independently. And we can do moving bodies, such as kind of flapping ellipses here. And so that's really cool. We have validation for this impulsively started cylinder at around 3000 here. We get accurate drag forces over time compared to literature. We get accurate vorticity profile over the boundary of the body, which is proportional to the viscous shear force. And we also get pressure reconstruction along the boundary of the body that is accurate compared to literature. We can do flow past the cylinder pair. This is validated with literature. What's nice here is that the reference solution domain is about 16 times larger than our domain size because we have this vorticity support that is compact. And so we only care about small domain size here. And we can evaluate pressure at any point on the body as a function of time. And then finally, we can do flapping foils. When I start the movement. So here we just impose the kinematics of these bodies. Okay, so I'm running out of time here. I just wanted to kind of showcase the things that we can do with our code in terms of moving and stationary bodies, everything up to second order accuracy in space and extendable to fourth order if we spend some work to upgrade the order of the finite difference schemes. I don't have time to go to the 3D, but I just wanted to show that basically we're working on an extension to 3D that exploits adaptive grid refinement, as well as runs on HPC architecture. So here's an example where we solve a transport equation on an adaptive mesh that is automatically refined based on the features in this flow. And so that's in progress. We're working on adding an elliptic solver to that. Okay, so in conclusion, we have developed a 2D vorticity velocity sharp interface method that can handle multiple stationary moving bodies. We have validated the computation of both the global forces as well as local pressure and shear loading on those kind of irregularly shaped bodies. And we're moving towards two-way coupling, where we get, when we can solve kind of self-propulsion problems, deforming boundaries, and also fluid structure interaction. And then on the 3D side, we have a scalable multi-resolution framework for wavelet-based mesh adaptation under development. And we're moving towards extending that with an elliptic solver and then doing 3D IAM flow simulations with moving bodies in an adaptive mesh kind of setting. So that's it. Again, James and Thomas they should be here, so they can handle all of the technical questions. And then Philippe and Mathieu are collaborators from Belgium that have contributed to the early part of the IAM development. So thank you very much, and I'm happy to take any questions.
Thank you very much, Wim. Very interesting presentation, and also for finishing in time. We do have time for a couple of questions. Maybe you can use the time to say a couple more things you wanted to. Any questions from the audience?
I just had one. My name is Matt Camone. I'm from Lam Research, and we do work with level set methods to implicitly represent surfaces. I wondered if when you couple the objects to have them move, do you foresee needing such methods to represent the surfaces and the way they interact? Or
yeah. So right now we can generate intersections from a level set. So if someone gives us a level set for a complex geometry, there's a way to get the intersections that we need to do our kind of sharp interface treatments directly from the level set. So that part is there. When we're moving bodies, so far we're just doing kind of rigid body motions that have imposed kinematics. So we're not really solving the two-way problem yet, where we solve a body that is actually deforming or due to the flow itself. So when we extend it to that, we are planning to use level sets as kind of the main descriptor of the geometry of the body and keep track of the shape.
Okay, interesting. And is there any people who've done that in the past already with level sets? For this couple,
they're used a lot in multi-phase flows for sure. When it's like flow, like water and air, for instance, on a free surface, or like bubbles in water. That's where level sets are extensively used. In terms of fluid structure interaction, it would depend a little bit how you deal with the solid mechanics inside. And so I think there's a couple of people that do Eulerian solid mechanics and Eulerian fluid mechanics, essentially as kind of a monolithic, not necessarily monolithic, but a single continuum formulation. And there, I think the level set is also the advantages to keep track of the boundary.
Okay. Yes, thank you.
Thank you.
Any other questions or comments? Okay, that keeps us on time. Thank you very much, Wim.
Thank you. Thanks again.
Thank you.